Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the current mirror circuits. So first of all, let us understand what is current mirror and why it is used. And for that, let me start with the current source. So if we take an integrated circuit, then it consists of so many amplifiers. And to bias these amplifiers, we require the so many current sources. Now the advantage of biasing the amplifier with the current source is that here the emitter current is independent of the beta as well as the RB. Moreover, by increasing the value of RB, we can increase the input impedance. So for that, this biasing current should be very stable. That means the value of this biasing current should not change with the temperature as well as the supply voltage. For example, if we take the case of the smartphone, then as the battery discharges, then there is a reduction in the supply voltage. So this current source should be able to maintain the constant current even if there is a change in the supply voltage. Well, fortunately, it is possible to design such current sources, but it involves the lot of circuitry. So for the amplifiers of the integrated circuit, we require such stable current sources. So instead of designing a stable current source for each amplifier, what is actually done is, one stable current source is fabricated in the integrated circuit itself, and using the current mirror circuit, the same current source is replicated. So this replicated current source has the same characteristic as the reference current source. That means this current source is as stable as the reference current source. And these current sources can be used to bias the amplifiers. So this current mirror is the active circuit which senses the reference current and generates the copy or the number of copies of this reference current with the same characteristics. Now here this I copy could be same as this reference current, or it could be either a multiple or the fraction of the reference current. That means this I copy can be equal to I reference, or it could be equal to n times I reference, or I reference divided by n. But in any case, it is as stable as the reference current source. So now let us see how it can be designed using the BJT. Now we know that the BJT can be used to generate the current source because the collector current IC is the function of the voltage VBE. That means by controlling this voltage VBE, we can control this collector current. So to generate this current mirror, somehow we need to sense this reference current and we need to convert this current into the voltage. And we need to apply this voltage between the base and the emitter of this transistor, so that this collector current IC is proportional to the reference current. So this is the way by which we can convert the reference current into the voltage. So here as you can see, the collector and the base terminal of the transistors are connected together. So basically it is the diode connected transistor. That means here the BJT acts like a diode. And here this reference current is applied at the collector terminal. Now here for a moment let us assume that this base current IB is negligible. That means here we can assume that this collector current IC is approximately equal to I reference. Now we already know the relationship between the collector current and the voltage VBE, right? So in this case we can say that this I reference or the collector current is equal to Is reference times e to the power voltage VBE divided by VT. So here this Is reference is the reverse saturation current of the reference transistor. And from this we can say that the voltage VBE is equal to VT times natural log of I reference divided by Is reference. So as you can see, here the voltage VBE is the function of the reference current. Now let us apply this voltage VBE to the base of the second transistor. So let's call this second transistor as the Q1. So here this voltage VBE reference and the voltage VBE1 are same, because here the base of the both transistors are connected together and the emitter terminal of each transistor is grounded. That means here voltage VBE reference is equal to VBE1. Let's call it as a VBE. And as we have seen, this collector current is the function of the voltage VBE. That means IC1 is equal to IS1 times e to the power voltage VBE divided by VT, where IS1 is the saturation current of the transistor Q1. Now here, only one thing which we need to ensure is that the collector base junction should remain in the reverse biased, because here this transistor Q1 should remain in the active region. That means the collector voltage should be always more than the base voltage. So by ensuring this, we can replicate this reference current. So basically here what we did, first of all we generated the voltage which is proportional to this reference current. And then we have applied this voltage as an input to the second transistor. And this second transistor generates the collector current based on the input voltage. So here the first transistor acts as a current to voltage converter, while the second transistor acts as a voltage to current converter. So here this collector current IC1 is proportional to the I reference, and let us also see that mathematically. So here this I reference can be given as IS reference times e to the power voltage VB divided by VT. So if we take the ratio of these two terms, then we can write it as IC1 divided by I reference is equal to IS1 divided by IS, because these two exponential terms will get cancelled out, right? So from this we can say that this collector current IC1 is equal to IS1 divided by IS reference times I reference. Now here, if both transistors are identical or they are the matched pairs, then the reverse saturation current of both transistors will be same. That means in that case, this current IS1 and the IS reference would be same. And in that case, we can say that this current IC1 is equal to I reference. So in this way, using this current mirror, we can replicate this reference current. Now in general, this saturation current is proportional to the area of the emitter base junction. So here basically I am talking about this highlighted area. So if the area of this transistor Q1 is 5 times the area of this reference transistor, in that case this IS1 would be 5 times the IS reference. And from the expression IC1 is equal to IS1 divided by IS reference times I reference, we can say that this current IC1 would be 5 times the I reference. On the other end, if the area of this transistor Q1 is 1/5 of the area of this reference transistor, or effectively 1/5 of the area of the emitter base junction of this reference transistor, then in that case this IC1 would be 1/5 of the I reference. So in this way, it is possible to generate the multiple or the fraction of the reference current. So now let us see how we can generate the multiple copies of this reference current. So this is the way we can generate the multiple copies of the reference current. So as you can see over here, the base of each transistor is connected to the base of the reference transistor, or more commonly, it can be shown in this fashion. So depending on the area of the emitter base junction of each transistor, the collector current could be either multiple or the fraction of the reference current. Now in the integrated circuits, the area is usually defined in terms of the area of the unit transistor. So here let's say A is the area of the emitter base junction of the unit transistor. So here the reference transistor has the area of A, while the area of the emitter base junction of this transistor Q1 is equal to 3A. So as we have seen earlier, in this case, the current IC1 would be 3 times the I reference. And the same current can also be generated if the 3 transistors are connected in the parallel connection. So here, each transistor has an area of A and the collector terminal of each transistor is connected together. So here, the current through the collector of this reference transistor is equal to I reference, and the same current will also flow through the collector of each transistor. That means here this current IC is equal to 3 times the I reference. Similarly, if the 3 reference transistors with the area of A are connected in the parallel connection, then the collector current of each transistor is equal to I reference divided by 3. That means we can say that here this IC1 is also equal to I reference divided by 3. So in this way, we can generate the multiple or the fraction of the reference current. Now, so far in our discussion, we have assumed that the base current IP is negligible. So now let us see the effect of this base current on the replicated current IC1. So here, both transistors are of the same area. That means here, the collector current of both transistors will be same. That means here, this current will be also equal to IC1. Now we know that the base current IB is equal to IC divided by beta, right? That means the base current of this transistor Q1 will be equal to IC1 divided by beta. Similarly, the base current of this reference transistor is also equal to IC1 divided by beta. That means the current which is flowing through this branch is equal to 2IC1 divided by beta, right? So now, to find the expression of this IC1, let us apply the KCL at this node. So applying the KCL, we can write this I reference is equal to IC1 plus 2IC1 divided by beta, right? That means IC1 is equal to I reference divided by 1 plus 2 divided by beta. Now usually the value of beta is very high. That means in that condition we can neglect this second term and the IC1 will be approximately equal to I reference. That means whenever the value of this beta is very high, then the base current IB will be negligible, and in that case this collector current IC is approximately equal to the reference current. Now let us see, instead of the one transistor, if there are 3 transistors with the same area, then what would be the collector current? So here we are assuming that the IC1 is equal to IC2 is equal to IC3. Let's say it is equal to IC. That means here base current of each transistor is equal to IC divided by beta. That means here this current is equal to 3IC divided by beta. And the current at the base of this reference transistor is also equal to IC divided by beta, right? That means current in this branch is equal to 4IC divided by beta. And of course, this collector current is equal to IC. So if we apply the KCL at this node, then we can write I reference is equal to IC plus 4IC divided by beta. That means collector current IC is equal to I reference divided by 1 plus 4 divided by beta. So instead of 3 transistors, in general, if the n transistors are connected, then this collector current IC can be given as I reference divided by 1 plus n plus 1 divided by beta, right? So as far as the value of n is moderate and the value of beta is high, then we can assume that this collector current IC is approximately equal to I reference. Similarly, now let us see the effect of this base current on this circuit. So in this case, the collector current through each transistor is equal to IC divided by 3, right? And same current will also flow through this reference transistor, or to be precise, through the collector of this reference transistor. So here this base current is equal to IC divided by 3 beta, right? That means for the 3 transistors, the base current would be equal to 3 IC divided by 3 beta. That means the current through this branch is equal to 4 IC divided by 3 beta. So to find the value of this IC, let us apply the KCL at this node. That means applying the KCL, we can write I reference is equal to IC divided by 3 plus 4 IC divided by 3 beta. Or we can say that this collector current IC is equal to 3 times I reference divided by 1 plus 4 divided by beta. So if we neglect the base current, then the collector current IC is equal to 3 times I reference. But with the base current, this is the expression of the collector current. Similarly, if there are n transistors are connected, in that case, this collector current IC can be given as n times I reference divided by 1 plus n plus 1 divided by beta. So as you can see, when the value of n is moderate and the value of beta is high, then IC is equal to approximately n times I reference. For example, if n is equal to 5 and beta is equal to 100, in that case, this IC is approximately equal to n times I reference, or to be precise, it is equal to 5 times I reference. But as the value of n increases, then there will be an error in the approximation. Similarly, in this case also, as we have seen, this collector current IC is equal to I reference divided by 1 plus n plus 1 divided by beta. So as the value of n increases, then this collector current IC would be less than the I reference, and the error in the approximation increases. That means here we cannot increase the value of n indefinitely. For example, if the value of beta is 100 and the value of n is also 100, in that case, there will be a considerable amount of error in the approximation. And in fact, the value of this collector current is almost half of this reference current. So it shows that even though with the current mirror we can make the copies of this reference current, but we cannot increase the value of n indefinitely. But there are ways by which the performance of the current mirror can be improved. So if you observe the circuit, then one more transistor is also added over here. So let us find out how it will improve the performance of the current mirror. So here we are assuming that the collector current of each transistor is the same. Let's call this collector current as the IC. So for the n transistors, the base current over here would be equal to n times IC divided by beta, right? While this current is equal to IC divided by beta. That means here the emitter current of this transistor Q is equal to n plus 1 times IC divided by beta, and this current would be approximately equal to emitter current. That means we can assume that this current is also n plus 1 divided by beta times IC, right? So if we see the base current of this transistor Q, then it will be equal to ICQ divided by beta, that is equal to n plus 1 times IC divided by beta square. And of course, this current over here is equal to IC. So to find the value of current IC, now let us apply the KCL at this node. That means if we apply the KCL, then we can write this current I reference is equal to IBQ, that is the base current of this transistor Q, plus IC. That means I reference is equal to n plus 1 times IC divided by beta square plus IC. That means we can say that this collector current IC is equal to I reference divided by 1 plus n plus 1 divided by beta square. So as you can see, now in the expression instead of beta there is a beta square. So for example, now if the value of beta is 100 and the value of n is also 100, then in that case still this IC is approximately equal to I reference, or I would say that there will be only 1% error. So with this configuration, there is a significant improvement over the previous case. Similarly, in this case also, if you follow the same procedure, then this collector current IC can be given as n times I reference divided by 1 plus n plus 1 divided by beta square. So by including this transistor, we can improve the performance of this current mirror. And very soon, we will take some examples on the current mirror on our second channel. But I hope in this video, you understood what is current mirror, why it is used, and how it can be implemented using the BJT. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.